All right, so we just finished quiz 2. We're going to be talking about watershed modeling today, and how many people have WMS with them today? Most of the class, that's good. So we'll spend some time just really quickly getting into WMS. But before we start with the program, I wanted to give you an overview of what we're trying to achieve with it. So a couple times this semester, I'm going to bring this same slide up. You know, like, what's the big question of the course? What are we trying to, as engineers, generate? Like, what does hydrology have to say to a civil engineer that we're most interested in? So what we want to know is, what is the runoff going to be for an area of interest? For a certain watershed, what is the peak flow rate and when does it occur? Because knowing that peak flow rate will enable us to size appropriate infrastructure to handle the flow. This is a rainy day. The stream levels are high. There's a lot of flooding out by where I live generally if there's any kind of serious rain at all. And the stream wasn't over the banks yet when I drove in today, but it could be. And one of the things that you need to have to avoid water getting onto people's roads is if culverts are too small, it can choke the flow. So that the channel has potential capacity, but if there's a really small culvert, then it could cause water backing up upstream and have the water overflow the banks, and that's unnecessary. So the big question of the course is, what is the peak flow rate? Or what is the runoff hydrograph? What are the runoff characteristics? And the things that we're going to, the more we can account for, the more accurate our estimate is. And you may remember this principle when we were talking about time of concentration. Does anybody remember which was the most accurate time of concentration method? It was the first one we talked about. Kinematic wave. That's right. Why was it the most accurate compared to the others? Like, just not the specifics, but like big picture. What made kinematic wave the most accurate method for calculating time of concentration? I'll just stand here all day long. Somebody has to guess. Put me out of my misery.
There's more variables that go into it.
More variables. Yeah, it's accounting for more things. So it's a model. An equation is a model. It's a numerical or a conceptual model that's predicting something. So the kinematic wave equation is a model for predicting how long it takes water to travel over the surface of land. And it accounted for the length of the travel, the slope of the surface, the roughness of the surface, the precipitation characteristics that correspond to the time of concentration. So it just accounted for a lot of things. So here, we're going to use different models for predicting runoff. And the same principle holds true. The more of these characteristics that we can incorporate into our model, generally speaking, the more accurate we'll be. So if we have some model that takes into account all of this full list of things I'm about to show you, then that's a good model. Sometimes, though, we don't have all the data, or sometimes we're in a hurry. So there still is some value from simpler models, and we'll talk about all the different possibilities. So rainfall. We want to have some sort of a good representation of rainfall. Otherwise, you can't be expected to predict the runoff from a watershed if you're not accounting for the rainfall that causes that runoff. So this is kind of a no-brainer. But it's not just the depth that is important, it's also the timing of the rainfall. So temporal distribution is, in maybe 15-minute increments, how much rainfall occurred up to this point, and now another 15 minutes later, and then another 15 minutes later. Because there are some methods we're going to use that just only account for the full lump sum depth of rainfall without really digging into the details of what was the temporal distribution of that precipitation. Spatial distribution just means that we looked at some figures related to this. Sometimes it'll be the same depth over the entire watershed, but then other times it's only raining on one part of the watershed, not the whole thing. And that can be a really important factor, and some models account for that. For localized precipitation within a watershed. Abstractions. So we have to ask, does our model account for the evaporation during the event, surface wetting effect, interception by vegetation and buildings? Does the model have an appropriate way of estimating the rate of infiltration? Like, if your model doesn't know anything about the soil type, then it may not be able to estimate the infiltration rate as accurately as if you do have hydrologic soil group defined. So some of the models we'll talk about don't account for specific soil characteristics in the watershed you're interested in. It just treats all watersheds as having pretty much the same soil. And, that's an okay assumption if you don't need your runoff estimate to be hyper accurate, or maybe it's an okay assumption if you're in a watershed that has typical characteristics, but there are some places that just have, for whatever reason, like an unusual amount of gravel. Like we saw that when we were looking at the Cabell County map, that there were some hot spots where there was gravel in certain locations. And so if we happen to have an analysis we're doing in one of those gravel heavy areas, but we're assuming that it has typical Cabell County clay and broken shale, then it's not going to be a very good estimation of what's really happening at that site. Antecedent moisture. We've seen the huge effect that it can have when you're adjusting the curve number based on either the typical type 2 conditions or really wet conditions, which are type 3, versus really dry conditions, type 1. So, are you accounting for those sorts of nuances can really give you a lot more confidence in your model and on the runoff characteristics it's predicting. So these three things together is going to be what allows us to link from rainfall to runoff. But then there's also the question of, when we know the runoff depth, how do we generate the shape of the hydrograph? And so maybe we have a unit hydrograph for the watershed itself, but most of the time we won't. And so we're going to have to use some sort of a synthetic unit hydrograph to give a temporal distribution to the runoff. One way around that, though, is to use time steps on the rainfall, and then having time steps in your rainfall will automatically give you time steps in your runoff. And that's one of the really powerful advantages that a model like HEC1 or HEC-HMS has over more simplistic models like, for example, the National Streamflow Statistics or the rational method, is that we don't necessarily have to use a synthetic hydrograph. And then models can also take into account the travel time that water experiences as it's flowing through the stream, delays that are called routing. And so the effect of not only time of concentration, but transit time as the flow concentrates together and then goes through a channel. So the reason why we care about this is for sizing things like culverts and bridges, and also for assessing the risk of flooding where property is being developed and managing the land use in floodplains. So here's a list of the models that we're going to use this semester in WMS. And there are other models it's capable of applying. Some of them are just specialized to certain regions. Like in Arizona, there is really excellent work that's done in Maricopa County, which I think that's the county that Phoenix is in. They've got some of their own models that are localized to Maricopa County, and I think WMS has those models built in, but since we're not in Phoenix, we won't apply that. The rational method, we've had some exposure to that in class, and it's based on hopefully having a good guess of C value. Here's a rational method. There are tables of C value which vary based on return period and sometimes the quality of the vegetation over land, but there's a lot of wiggle room on these C values, and it's a little bit subjective. And even without the subjectivity of the C values, the rational method tends to overestimate the amount of runoff that'll actually occur. So we have to keep that in mind, that properly applied, the rational method is conservative, but it also has limits because we can only apply it to catchments that are less than 80 hectares in size. And a lot of the watersheds we're interested in are much, much larger than that. So the National Streamflow Statistics is a product that's generated by the USGS, the United States Geological Survey, and every state has a different publication. And West Virginia's publication, I think the most recent edition of it comes from 2010. Although it wouldn't surprise me if a new update is in the works. I think the most recent one for now is 2010. And it's a really interesting approach for very simply with only a couple of variables. In West Virginia, there's only one variable, trying to determine what would be the peak runoff for a watershed in the case of West Virginia based on area. I mentioned Arizona a few minutes ago. The NSS model in Arizona takes the area of the watershed into account and then also the elevation because it's mountainous and of course we already know about orography, the orographic effect that the higher you are in the mountains, the more likely it is that wind going up over that mountain is going to have enhanced precipitation. And so they kind of account for those high altitudes getting more moisture in the Arizona regression model by having a two-factor model that takes the area of the watershed and its altitude. But let's focus on West Virginia for now. Here is a map of stream gauges in West Virginia. And directionally, there are about 100 of them with enough data that they were included in a statistical model. And what they did was they said throughout the state, we've got these gauges. Some of them have been around for 15 years, some of them around maybe 70 years. I don't think any of the stream gauges, well, maybe the ones on the Ohio River have been around for 100 plus years. But that's the exception. The problem is always that the gauges haven't been around long enough and that there's not very many of them. You know, West Virginia is a pretty big state and we've got approximately 100 stream gauges. And so what they did was they said, well, how big is the watershed that's feeding water into the stream that this gauge is measuring? And then they went back through the records and they tied together the precipitation data that's historically available with the stream gauge data that's measured at those locations and looked at it that way. And then they also just looked at it in the probabilistic view of if you've got 100 years of flow data, then you know that in 100 years of flow data, then the biggest runoff that you saw is the peak runoff for the 100-year storm, statistically speaking. It could have been that that was the 500-year storm, it could have been the 1,000-year storm, or maybe it was just the 50-year storm because it was an anomaly and you never had a 100-year storm during those 100 years. There's a lot of uncertainty with statistical data analysis like this, but the USGS did that whole analysis. Let me dim the lights a little bit more so it's easier to see. They divided the state up into 3 regions. There's the western plateau, which is where we live. There's the central mountains and the eastern panhandle. And they said that broadly speaking, there are 3 distinct kind of runoff zones. I guess the central mountains have all about the same altitude and some distinctive precipitation patterns that are a little bit different from the lower lying areas in the state. And then the topography in the eastern panhandle is really flat. You know how we have basin slopes between 35 and 50% for most of the watersheds in Cabell County. Out in the eastern panhandle, they have a lot of watersheds where the basin slope is less than 10%. So it's much, much flatter out there. So because of that, it may not be that the precipitation patterns are necessarily hugely different, but the water concentrates more slowly for a given area. So they looked at the stream data. These are all stream gauges. These aren't rain gauges. They looked at the stream flow data, and they created equations that predicts what is the runoff in terms of cubic feet per second for a 1-year storm, a 5-year storm, a 2-year storm, a 10-year storm, and so on. And so the way that it works is that you would assess what is the area of the watershed in terms of square miles. And so if you wanted to know in the eastern panhandle, for example, what's the 25-year peak runoff, it would be 204 minus the area of the watershed in miles to the power of 0.848. And then all of this data just talks about the goodness of fit, or kind of the statistical quality of the estimate, that the standard error is going to be about 20%. So anytime you make an estimate with this, your standard error is 20%. By the way, AOP is it's talking about the probability of experiencing that peak runoff in a given year. So a 25-year storm, for example, PK 25 means we're calculating the peak runoff for a 25-year storm. That means that in any given year there's a 4% probability that you would experience that runoff rate. So we've got different equations for the eastern panhandle than for the Central Mountains. Same thing in the western plateau, different equations. And every state has equations like this, where a lot has not been accounted for. Like for your watershed of interest, if you use this model, you're not putting any specific land use details. Now, by the way, this is saying it's for, if we look at the title of it, rural unregulated streams. So you can't use this to predict what's going to be the flow rate in the Ohio River, because the Ohio River is regulated. There's all kinds of locks and dams controlling the flow. So this is for rural unregulated streams. So if you have an urban watershed, so 1 square mile in Huntington is not going to be, you're not going to get an accurate estimate of the peak runoff for 1 square mile in Huntington, because Huntington is far more urban than the average rural unregulated watershed. So that's just another kind of asterisk, is that if you are analyzing a watershed that has a lot of urban area in it, then you may not get great results from national streamflow statistics. So we talked about rational method. This is national streamflow statistics. The rest of the methods use the NRCS curve number model at the heart of relating soil type, land use, and the amount of precipitation excess. And then the methods differ in that either you're looking at one complete rainfall depth in a single step and calculating the runoff from that, and then using a unit hydrograph, or you're breaking it up into time steps of rain. And so the TR55 uses just the overall depth of precipitation and a unit hydrograph, whereas HEC1 and HEC-HMS both use precipitation time steps in an effort to get some enhanced accuracy. So let's open up the program just so that we get a little bit of exposure to it today. I haven't yet updated this computer to 11.2, but I think that the controls are going to be largely the same from 11.1. You're on version 11.2, right? That's what you've got? By the way, I'm going to blow Bryn's cover. She really knows how to use this program really, really well. She worked on it over the summer. Bryn is probably more of an expert on WMS than I am. So if you ever need help, Bryn Brown probably knows how to do it in WMS. She did just about everything that we're going to go through this semester, with the exception of stochastic modeling. So you will still have a chance to learn a little bit more with the stochastic modeling. Okay, so this is a GIS system where the beauty of this is that it'll go and fetch the data for you and process the data and set up the model. So it's what's called a pre-processor and a post-processor. As a preprocessor, what it's doing is it's obtaining the data that's needed for the HEC1 model to be run. HEC1 is really old. It's like from the 70s. There's nothing really fancy about the engine, the hydrologic engine, but what WMS has improved on over the years is making it just increasingly simple to set up the model, where to generate a HEC1 model in the 70s when it first came out took weeks and weeks. But I could set up a HEC1 model now in like 5 minutes that would have taken weeks in the 70s. So Post-processor means that after it does the watershed calculations, we can use it to visualize hydrographs. The main button that you're going to want to be familiar with here is the hydrologic modeling wizard. It looks like a little wizard's hat on top of a couple of little dots here. Hydrologic modeling wizard. If you hover your cursor over it, the label will come up. So just to show you a couple of things about the program, let's start this wizard, because you can do all of these steps manually, and that's how I learned this program a long time ago. When I first used this program, it was 25 years ago. So it's improved a lot since then. We didn't have the wizard when I started using it. So we'll start the wizard, and the first thing we have to do is save the file, because as good a program as it is, it crashes occasionally. And you're going to want to have your work saved as often as you can. And so there's just a couple of little foibles it has, and I'm going to try and remind you of these foibles to avoid problems. You probably need to save your files really close to the root of the hard drive's directory. Let me show you what I mean. Don't save it in your OneDrive. Don't save your files in the OneDrive, at least not initially. When you're working on it, save it on the C drive. And my suggestion is to create a folder in the root of the C drive that's just called like temp, or here you can see one that's called WMS files, because sometimes because HEC1 and other models are so old, they get confused if you're in a subdirectory buried inside of another subdirectory and another subdirectory. Like it just, it can't follow the file location to an infinite number of subfolders. So it's better if you here browse to a location. Let me browse to a location that's just, yes, I want to replace it. Browse to a location that's pretty close to the root. So like C WMS files, and then I'm going to create one that's demo 2024-02-28. So today's date. And I'll just call this class demo. And save it. And you have to click save. Like once you've just defined the file path, it doesn't necessarily save it automatically. You have to click save, and then it'll change the name up here at the top. So you'll know that it successfully saved it. All right, now probably if this is the first time that you are running the program, it doesn't have a projection defined yet. And the thing to know about projections is that the Earth is not perfectly spherical. It doesn't have the same circumference around the poles as it does around the equator. And because it's not perfectly spherical, there's all these different attempts to correct for the irregularities of the Earth's shape. And also a lot of different unit systems that are used to define location. So you're probably already familiar with latitude, longitude, you know, like GPS coordinates of degrees, minutes, seconds. But there's a lot of other coordinate systems as well. So you have to define which coordinate system to use. And so instead of, I think initially it'll say no projection, you need to select global projection and then set, and it'll give you a whole list of options to choose from. We want to use NAD 83 UTM zone 17. The entirety of West Virginia is within zone 17 north of the Universal Transmercator projection, UTM. The Universal Transmercator projection is just a way of accounting for the shape of the Earth. And then NAD 83, it's some sort of a national altitude data set where the coordinate systems are locked to certain points on the map. And so we'll have X and Y defined by that. Was everybody able to find that projection? No? Okay, so go under projected coordinate systems. So expand the projected coordinate systems list, and then expand UTM. Go down to North America, or if we could just go straight to NAD 1983. So NAD 83 UTM zone 17. Now did you find it? Okay. The good news is you only have to define this once. Next time you open the program, it'll kind of remember what you did last time. And then vertical, change it from local to NAVD88. So that is, instead of a horizontal coordinate system, it's setting a vertical coordinate system, so what altitudes are based on, and then switch it to units of meters for the elevation. These are some of the boring preliminaries that if we don't get right, then our watershed areas could be wrong, maps could show up in the wrong location. Like if you import a picture and you know it's supposed to be a picture of your watershed, but now the photo and all of the data are in two different locations, most likely it's because the projection has been set incorrectly. So once you set those, then the next thing we're going to do is define the boundary of the watershed area that we're interested in. So right now, this is just, it doesn't have any coordinates specified. These are like the four corners of the map that we want to be working in. And if you click Define Project Boundary, the first time you do it, it may not automatically pop up like that. You may have to kind of down here in at the bottom ribbon, kind of minimize WMS and then bring it back up again. You may have to just play around a little bit with bringing WMS into the background and then back into the forefront again. Eventually, I think that you'll get it visible. All right, so this, oh, I've messed around too much. I'm going to wait for it to respond. What map view do you have when it first comes up? Does it show the entire United States or the whole world? Anybody got it pulled up? You got the world? Kind of toggle it once or twice and let me bring it up again. All right, so here it is. You could type in a location like Huntington, West Virginia, and jump to the location and it'll automatically go there for you. Or you could type in the latitude and longitude and click jump. If you know like the GPS coordinates, then it could jump in that way as well. So everything that is shown in the window right now is what it's going to go and get GIS data for. But the problem with zooming out really far is that it's going to force it to download a lot of GIS data, and it would take a long time. So zooming in on just the watershed you're interested in is the way to go. So remember in the previous class we were talking about the Boy Scout camp that is between Milton and Barbersville. So let's try and here's Ona. So look, here's 64, and if we just zoom in on Boy Scout camp area, let's say we wanted to delineate and characterize this watershed. We can kind of see where the ridge lines are from this map that's brought up on the screen. So what we'll do on Friday when we get back together is we're going to go through the process of obtaining elevation data, obtaining soil type data, land use data, aerial maps, and we're going to go through the process of identifying a watershed and then determining its characteristics. So you may have to close the program and start it again, but try to get to the point to where you're able to type in a location and it'll jump to that location on the map for you. Because once you have a location specified and you click OK, then it fills in the coordinates here in this window. All right, so just to revisit the announcements one more time, Homework 7, which covers the web soil survey stuff that we did before, is due on Friday.